Yeah, hello and welcome to my talk, Breaking the Industrial Internet of Things. I'll talk a bit about hacking industrial control gateways. But first, a short introduction. Who am I? My name is Thomas Roth. I'm the founder of Level Down Security, a small security consultancy from Germany. My main focus is on embedded devices, from trust zone to bootloaders to industrial systems, all kinds of stuff. And if you want to follow me on Twitter, you can find me at Stack Smashing. And if you want to send me an email, feel free to mail to thomas.roth@leveldown.de. So before we start, all information in this talk is based on reverse engineering. So if there are small mistakes, small misinterpretations, I apologize. I did my best to get everything correct, but you know how it goes sometimes. I'm also not trying to shame any single vendor. So the vendor selection of the devices we'll talk about is completely random, and I think the entire industry has a problem and not a single vendor. Also, all scripts that were used in the research are available on GitHub, but the exploits are currently not, because there are far too many devices out there that are unpatched currently. There are some people who talked about a similar class of devices previously. For example, Mr. Ray Whiteman, Patrick DeSantis, and Maxim Rupp. You absolutely want to check them out if you're interested in industrial security, and they have been very helpful to me in providing some feedback, giving me additional information, and so on. So let's talk about the motivation for this talk. I was doing a pen test of an electricity provider, and they showed me all their SCADA systems. They showed me how they're interconnected, how all their substations are connected to this big control room. And then they showed me basically a shelf full of tiny devices which had a serial port on one side and Ethernet on the other. And they were used to basically interconnect a ton of devices via RF links, via Ethernet, via GSM, and so on. And they all came back at that single point. And I found them very interesting because they are really at this place between the native protocols such as serial and so on and the internet. Also, industrial systems are used as weapons nowadays, so we really need to look at securing these devices. So we have attacks on steel plants in Germany. We have a cyber attack on a Saudi Arabian petrol plant, which almost caused it to explode and was actively used to cause harm, basically. We were lucky that the exploit was not working. And we also have active attacks on the power grid. So for example, the Ukraine power grid attack in December 2015 was conducted using one of the devices I'll be talking about today. So what is industrial IoT? If we look at traditional ICS networks, they're kind of this enclosed system. You have, for example, a chemical plant, you have a control room, you have all your actors, all your sensors located in a secure perimeter with physical access control and so on. But today, if we look at electric grids, if we look at large chemical plants or large plants in general, suddenly those kind of segmented networks become a very wide area network. So you might have, in the case of an electricity grid, you might have solar panels that are remotely connected for data collection or for control. You might have some PLCs in your substations that are connected via some kind of WAN to your central control room. And there are all these kinds of things. So for example, substations, we have remote valves, we have water dams. So for example, the water dam in the city where I live is remotely controlled via one of the devices we're going to talk about. We have traffic management systems, we have access control. So for example, these barriers are often connected via such devices, and even tunnels, which was kind of funny because I was doing a pen test and I asked, hey, I found this device, it's vulnerable. What the hell is it? And they told me it's a tunnel. And so it turns out that the ventilation system of tunnels is also remotely controlled. And so if you manage to break into this and stop the ventilation system, chances are high that you might cause someone to suffocate or similar. Alrighty, so industrial control systems. As I've mentioned before, they used to connect different protocols to an IP network. So in the industrial control world, you, for example, have Modbus, you have RS-232, you have CAN bus, AS-485, whatever. And all those protocols somehow need to talk to a computer. And for that use case, these industrial control gateways are used. And they connect via Ethernet GSM, whatever, and you can basically find them in any larger industrial installation. And the first feedback I get when I talk to people about the industrial gateways is, hey, don't worry, these devices are air-gapped, they are on a secure network, whatever. But how can a device with an antenna be air-gapped, right? I mean, these devices today have Wi-Fi, they have GSM, they have some proprietary radio systems, they use LoRa, they basically can do everything. And even the vendor examples, the same vendor that tells me, no, these devices are air-gapped, their examples, for example, use GPRS to remote control valves, to remotely monitor systems, and so on. So in this case, from Advantech, and Moxa has the same examples of remote controlling pumps and whatever. And so these are not only used to gather sensor data, they're actively used to control things remotely. And so these devices are absolutely not air-gapped. And then if you go on the internet and start scanning a bit, you find thousands of these devices open on the internet. You actually can find entire network ranges almost exclusively filled with these devices because they come from industrial ISPs. And most of them are significantly outdated. So for example, on Shodan, you can find 8,600 devices of just a single type. And even if they are not fully open on the internet, the barrier of access to them is mostly very low. So you might have SIM cards with public IPs, as that there are some providers that provide you with industrial SIM cards and they give you a public IP. And if you look at their whole RIPE range, you can just find hundreds of devices open on the internet. Often they use static IPs without any VPN protection also, or they're connected via Wi-Fi. And in one case, we found an industrial Wi-Fi, which was a point-to-point directional Wi-Fi with the IP, with a password sent to 11111F. Then you have the issue of physical access. For example, in these small boxes, it's trivial to break in. We've got good lock pickers here at Black Hat, so this is not protection, and we need to make sure that these devices are even secure or at least in some way tamper-proof. Or what we also see is that these devices are connected via GPRS with a custom APN, so they are basically in a custom network, but they are not really segmented in any way. So if you steal a single SIM card of one device, you can connect into the entire SCADA network. Okay, that being said, let's start hacking some gateways. So all equipment that was needed for everything you see in this talk is just a simple oscilloscope, a cheap logic analyzer, a bus pirate, a multimeter, and a laptop, and obviously a soldering iron. I have this slide in here because some of the vendor response was these attacks on like the resources you need to conduct an attack on industrial network are so high, nobody can do it. So this is me doing it at home. So the first step before I actually got started was I needed to find potential targets. My personal process is the first thing I look for is, can I get the firmware before I even start? So I check the vendor sites, I check whether I can download the firmware, I check if the firmware is encrypted, and then I check the acquirability. So basically, how expensive is this research going to be, and how expensive is it going to be if I break it? And also, it should be a half-watt current technology, because otherwise you just hack junk, old junk, and that's not really interesting. So if you do this for a couple of weeks, you eventually have a collection of random industrial hardware interconnected on a board. And these are the devices plus some new ones that we are going to look at. The first device I would like to talk about is the Moxa W2150A. It's a simple Ethernet or Ethernet to CAN and Wi-Fi adapter. And you can get this very easily. It's used a lot around the world. And what's nice about it is you can find the firmware publicly. It's decently cheap on eBay. And it's found a lot in the wild. And so the first step was, as I've mentioned before, let's get a firmware of this device. So what do you do if you find a random firmware? The first thing is you run strings on it, just to see, is this encrypted? And unfortunately, the only thing that's readable is the model number, and that's it. Otherwise, it's just gibberish. The next thing we do is we run a tool called binwalk. Binwalk tries to detect signatures of common compressions, of common firmware structures and so on, but in this case not a single hit. So maybe it's encrypted, that would be kind of bad. And if you're not sure if a file is encrypted or compressed or something, what you can do is you run an entropy analysis on it. And an entropy analysis will tell you if the device has a high entropy, so it's very random, it means that it's either encrypted or compressed. And if it has low entropy, it's very likely to be unencrypted, just because machine code is not dense enough to really be random. So you will very easily see the difference between an unencrypted and an encrypted image. So as you can see on the graph, it looks like a straight line with high entropy, so not looking good. But then I remembered that when I downloaded the firmware, there was a small note on the bottom of the site, which basically said, before upgrade to firmware version 2.x, please make sure you have already upgraded the unit to version 1.11. And if we go to this download link, you see that in the changelog, they actually introduced the support for encrypted firmware. And so I decided to download this older image, and sure enough, if we run strings on it, you can see it's fully unencrypted and we can use it for analysis. And if we just run this image into a hex dump, you can see that almost every fourth byte is an E. And that immediately tells you that you're looking at an ARM firmware. Why is that? Because the first 4 bits of any encoded ARM instructions are what's called the condition bits. So basically in ARM, every instruction can be set to only execute if a certain condition is met. So for example, if the carry flag is set, if the 0 flag is set or so. And because mostly you just always execute, every 4th byte will be E. And so we know that we have an unencrypted firmware with ARM code. And if we run binwalk and our nice entropy analysis on it, we can see that indeed binwalk finds a lot of compressed data, it finds a squashfs file system, it finds gzip compressed data, and so on. And so, wonderful. We can hopefully use this to find the firmware upgrade code and see how does this encryption of the firmware upgrade actually work. And after browsing a bit through this decrypted firmware, I sure enough found a small file called helpfully libupgrade firmware. And Moxa was nice enough to not remove any of the symbols, so we can actually find a very nice function called firmware decrypt. Thank you. And so I loaded the whole code into IDA Pro to look at it and to disassemble it. And what you can see on the left part is that there's a lot of there are a lot of XOR instructions. And if you see a lot of XOR instructions in something, it already tells you it's very highly likely that there's some kind of XOR decryption happening. And so basically in this case, it loads a constant called password. And it goes into this kind of loop, runs a lot of XOR on this constants, and then eventually goes out of the loop and calls a function called ECB128 decrypt. This sounds a lot like an AES decryption, and there's no single asymmetric crypto or anything involved. So that means if we can get this AES key out, we can not only decipher the current firmware, but we can also create new firmware, because there's no asymmetric check of the firmware. There's no hashing, there's nothing to really prove that the firmware upgrade came from Moxa. And so I went ahead and basically implemented the whole thing that I saw in assembler in C and ran it, and sure enough, we got the full password, which is 2887con7564. And this, combined with a script I called Moxa decrypt, allows us to decrypt the full firmware, and we can run binwalk on it, and sure enough, we get the full decrypted firmware, including all compressed ranges, all squashfs file systems, the kernel, and so on. The scripts for this can be downloaded at my GitHub, by the way. And yeah, so after I knew I can decrypt the firmware, it's a device I can buy everywhere on eBay, it's a device that is cheap enough for me to look at, and it's widely used, I decided to buy it and immediately open it up. So inside this device you will find a Freescale automotive processor, which is just your standard off-the-shelf ARM processor, mostly used in the automotive area or in the industrial area. And inside of the device, we also find a ton of test points. So for example, basically all exposed pads. I tested them with my oscilloscope. I hooked up a logic analyzer to them and tried to find a serial console. And sure enough, if we look at those 4 pins, we have a full serial console. And if we connect our serial to USB adapter to it, we get a wonderful root shell without any authentication whatsoever. And so at this point, we're in this great position that if we get access to the hardware, we have full root access. And if we, let's say, start to write an exploit, we can actually debug it directly on the device, which is a pretty nice situation to be in. And so this is not really a vulnerability, this is a design decision. So we needed to look at all the interfaces that are available for potential remote vulnerabilities, because this is kind of standard and kind of boring. And so, yeah, I looked at all the available services, and if you port scan this device, you will see that there's a web interface, there's Telnet, SNMP, some serial driver protocol, and also a proprietary configuration protocol running on port 4900. And I started with looking at the web interface, and it's really, really bad. So if we look at the list of vulnerabilities, we go from cross-site scripting in every field to cross-site request forgery to unsecure authentication to command injection to Stack Overflows over to a 0-day for the web server that's publicly on the internet. So, demo time. I had to pre-record it because my SCADA hardware is stuck in US customs. So. Okay, so yeah, this is the web interface, and I'm just logging into it with the credentials. And when you log in, you just see the standard overview of the system. You see the model name, the serial number, and so on. And if we go to the basic settings, we see some nice text fields. And what do we do as web pen testers when we see a text field? We paste some JavaScript in it. What else? And so in this case, just some alert. We press apply, reload the page, and we get JavaScript execution. And if there's a single thing on the page that tells you a lot about this class of devices, it's that it's best viewed with Internet Explorer 5. This is a firmware released in 2017, by the way, so it's not like old firmware. This was like very up to date. But okay, these are authenticated bugs, so that's kind of boring, right? If we want to have real vulnerabilities, we want something remote and we want something unauthenticated. And so I decided to look at this custom protocol that is used for firmware upgrades, and my goal was to reverse engineer it and build a fuzzer. The goal of a fuzzer is to basically take valid input data, mutate it in some way, send it to the device and see if it crashes. And because we already got code execution on the device via the serial interface, we can also basically start handling all these crashes and immediately get great intelligence of the crashes. But this turned out to not be necessary, because while developing this fuzzer, I accidentally sent too much data to the device. I basically made a small mistake in my loop, my packet was too long, and guess what happened when I sent a lot of A's to the device? Obviously, Stack Overflow or program counter is set to AAAA, and we basically have a trivial to exploit Stack Overflow in like half a day of exploit development time. Demo time. So I packed this whole thing into a small Python script. I can just point at the IP of the device, and if we run it, it will spawn a shell on the server, and we can just use netcat to connect to it. Paste the commanded outputs, and then you can see uname A, Linux kernel 2631, and we are in as root. Very easy. So obviously these bugs were reported by the vendor, and some of these bugs were actually reported by different people before on slightly different devices. And so what it turns out is that if you report a bug to some of these vendors, that if you find a vulnerability and you send it to them, the vulnerability gets fixed, but then there are like 2, 5, 10 different devices which almost run the same firmware, which stay completely unpatched. So they only, you can, like for example, the cross-site scripting bugs were reported on I think 5 different devices, but they are still on some of the new firmwares. And so this is a whole security culture problem from my view. And you can see this, the device on the right is called a secure router or something from Moxa, and it has the same basic bugs as the cheaper ones, which are not from the secure edition. So basically these, yeah, you can find these bugs all across the product range, unfortunately. So the next device I looked at was the Advantech EKI-1522, which is kind of a similar device. It's just a serial to Ethernet device. You can also get it with Wi-Fi. You can get it with GSM, I think, or with more Ethernet ports, whatever. And it's really just a simple device. And so as before, the first thing I did was I looked at the firmware of the device. Running it through binwalk and through the entropy analysis, we immediately see very low entropy, some high entropy regions, so it's probably unencrypted and just compressed. And we can see that binwalk even immediately detects the Linux image and so on and so forth. And what's kind of interesting after looking through the firmware is that it runs a web server called BOA, whose last release was in 2005. So a device you buy in 2018 runs a 13-year-old web server. And the main binary found on the device that handles all the serial communication, all the web server and so on, is called edgserver. And edgserver, when I look at such a binary, I look at calls to what I consider dangerous functions. So for example, string copy, sprintf, and system. Because all these calls, system either gives me remote code execution, and sprintf gives me buffer overflows, and string copy gives me buffer overflows. So if I find lots of these, I'm already pretty confident that I'll find something. And this is, again, before I even bought the device, I looked at it, and sure enough, I found in the firmware a long string which looks a lot like a mail command. And you can see that there are a lot of parameters that are filled in. So, for example, there's the %s will insert a string of arbitrary length, and so on. And this is, from my interpretation at the time, this was the alert mail system. So if you have a failed authentication, this will send you an email with the details. And if we look at where this string is used, it's used as an argument to sprintf, which first doesn't check buffer sizes. So if we manage to put in a very long string, it will overflow the buffer. And then after the call to sprintf, it actually will call system. So if we manage to insert anything into the mail subject, for example, the username with which we failed the authentication, we will get remote code execution very easily before we even bought the device. So at this point, I again decided to go on eBay, find a device, buy it. And the fun part here was that I first bought a device which was slightly older, where this mail functionality was broken. So the bug was there, but the mail system was broken for whatever reason, and acknowledged by Advantech that it was broken. And so I had to buy yet another device on which the functionality actually worked. So, okay. So I looked inside, I checked all the paths, and again, for sure, there was a serial console as root without any authentication. And again, like if the file system and so on these devices are not read-only. Like if you change something on the file, for example, you can buy it from a distributor, you can modify the device via the serial console, send it back, they will happily resell it. We've tried that with the allowance of a distributor, that we basically got a device from them, modified it by creating a file, sending it back, and ordered it again. And for sure, we got the same device precisely again with our modifications. So we actually have supply chain issues because of these serial consoles and because there's no way to actually authenticate the device and check whether it's been tampered with or not. So again, how do we find vulnerabilities? We have a web interface, we have a proprietary configuration protocol, yet again, we have Telnet, we have SNMP, and again, a custom serial driver protocol. And again, I started with a web interface, and again, we find cross-site scripting, cross-site request forgery, command injection, everything, and even broken authentication. And this is kind of a fun bug, because if you unlock the admin interface from one computer, it somehow unlocks it for everyone. So you log in from computer A, and everyone else can also log in without any password or so. I don't know how that can work, but yeah. And then we also have a Stack Overflow again in another protocol, which we're going to look at in a second. But first, let's look at the web interface again. So we log into the web interface again with default credentials. By the way, if you ever do a SCADA pen test, 50% of the time the default passwords will work. Like, I don't know. And in this case, we again go to the system configuration. We have a nice device description field. We enter some JavaScript in it. We save it, and we reload the page. And again, we get a JavaScript alert. So again, trivial web vulnerabilities in an up-to-date device. Did it finish running? Yeah, good. But web vulnerabilities are kind of boring. So let's write an exploit for the Stack Overflow. Again, because we have GDB, we have serial console, we can install GDB, we can just debug our exploit. It's very trivial to write once you have the Stack Overflow. And so for sure, I again wrote a Python tool which just takes the IP, spawns a shell on the device, and you can just use netcat to connect to it. And you see, again, it's like an old Linux 2631 built in, I believe, 2017, and we are logged in as root remotely. And this is because all these services, the edge server, the web server, everything runs on as root on all these devices. So there's really no permission system or anything. Everything runs as root, everything runs on outdated Linux kernels, everything runs on outdated web servers, and if any of those components fail, you're root on the machine. So let's look at Lantronix devices. So this device is called Lantronix EDS2100, and it's a simple serial device server. It has 2 Ethernet ports, and it, as the only device in this talk, it doesn't come with Linux. So I used something called Evolution OS on it. I have no clue what Evolution OS actually consists of, and yeah, I looked at the firmware of it, and it was unencrypted, yay again, and using the Coldfire architecture. And Coldfire, I've never worked with it. It's pretty hard to find a good disassembler for it, so this was for sure going to be interesting. And there are also no obvious external software components. Like if you look in the firmware, there's no OpenSSL, there's nothing you really know or can research. It's pretty much all proprietary from what I could tell, or purchased in from third parties. And so I decided to still buy it and give it a spin, and bought the device. And for the first time, I couldn't find a serial console. There's something that looks like a debug port, but I could not get it to debug or give me any serial console or anything at all. And I don't even know, to be honest, whether Evolution OS even has a command line or anything. I have no clue. And so this made this device much harder to look at, right? Because you still have a web interface, you have a telnet which runs with custom with a custom menu basically, and you have SSL, SSH, FTP, TFTP, and this device was the first one to really have strong security configuration options. At least there's a guide on how to really configure it securely, on what to do, on what not to do, and the web interface was also a bit more stable, and so I just found cross-site request forgery, a configuration injection, and also an authentication bypass. No code execution or anything, just because it doesn't look like the system actually is executing commands or anything in a shell, because it's custom. So demo time. As said, device authentication bypass. In this case, if you look at the device, it requires a password. We don't know it. And so I wrote a small tool, which is the video running? Yes. Which I called Lantronix pawn. And if we reload the site, just press cancel, we are in. So we got a nice authentication bypass because of a bug in the web server. So device 3 broken basically. The next one I looked at actually was the Schneider device, the PowerLogic EGX100, which is an Ethernet to Modbus gateway. And Modbus is used a lot in ICS applications. And again, we had trivial web vulnerabilities. This, unfortunately, is the last device I bought, and so I'm not fully yet through the vulnerability disclosure process, so I cannot demo this yet, but I can tell you that you will find this device a lot in the wild, and there are a lot of very, very funny issues in it. So hopefully soon. Then, kind of a different gateway. At the beginning of the talk, I showed all the different radio protocols that are used in the wild in the industrial IoT field. And at one penetration test, I found this GE MDS system. So this is a custom, a proprietary radio solution for basically connecting serial devices or Ethernet devices via RF. So via a custom radio, you need licensed spectrum to use it. So for example, if you are an electric grid provider, whatever, then you need to go to the state, license the radio band, and then you can use it. And it has optional encryption. On the old devices, you actually have to buy a special box to enable encryption. And on the new ones, it's integrated, and it's used a lot on electric grids and also a lot on water dam systems. So on remote water dams, they use this kind of proprietary radio. And if we look inside of this device, we can see that some of them contain a compute module, or they contain a flash that you can read out. And the flash is not encrypted, so you can read out the encryption key from the flash. And because the whole system is based on a pre-shared key, if you own a single device of these, you actually own the entire network. So we have a key extraction attack, which allows full decryption of the traffic with these devices. And I've also got a GNU radio module coming up soon, hopefully. So I reverse engineered the whole radio protocol, which is a QAM-based protocol, and so hopefully soon we'll have that on GitHub. And yeah, broken too, unfortunately. So what's the answer? Obviously, let's use VPN. But then if you look at the VPN stacks of all these devices, you will want to cry. You have broken IKE parsers, you have bad crypto support, you have SSL issues, and on one device I enabled VPN for everything, and then the configuration port was still exposed without VPN. And I sent the vendor an email and said, hey guys, how the hell do I turn this off? And the answer is, no, we need this in case the VPN fails. Thank you. Yeah, so before we finish, some other devices are even worse. Like, I looked at some vendors, but I don't want you to get the impression that the others are better necessarily. Quite some devices that are out there run ECOS, which is like a real-time operating system, which had its last release 9 years ago. No memory protection whatsoever, no thread separation, nothing. Some devices run Linux 2.4. that you can buy today, and they still ship software updates. I imagine they have like a very old computer somewhere in the closet where they go to build a new software release for this. I don't know. And some others even have unfixed public vulnerabilities. And for example, you can find a lot of cheaper serial to Ethernet gateways on eBay they all look the same, but they all come from different vendors. So I guess it's just some ODM situation. And this thing even has backdoor SSH accounts. Like if you serial console it, you can see that there are backdoor accounts everywhere around it. So we really have an issue. So to summarize, shit's on fire. we have no integrity protections on any of the devices. Like, we literally cannot ensure that the device has not been tampered with or supplies the original firmware. And for example, if you look at the firmware download portals, they are crazy insecure too often. For example, on Schneider, we had trivial cross-site scripting, which can be used for phishing attacks. So you can just send somebody an official Schneider link and provide your own firmware. We have no attestation functionality, no security mitigation. So if you look at it, there's no ASLR, there's no NX, it's like exploiting in the 90s, really. And from my perspective, there's also, unfortunately, not really a security culture with a lot of these vendors. Not all of them. After I first talked about these devices, a lot of vendors, including Moxa, contacted me and were very nice and very engaging in the whole process. But yeah, I still think these are big issues. So with that, thank you very much for coming, and I hope you enjoyed this talk.